All right, good morning, you guys. Today, happy Friday. It's Friday, April 17th. Hopefully, you guys had a good week. Hopefully, you guys are excited about a little bit of decent weather this weekend. Supposed to start warming up a little bit, so it'll be good to get outside, get a little fresh air, and hopefully not feel so cooped up. What we're going to finish up our school week with is section 6. So we're skipping section 5. It's kind of an application problem. It's not that terribly important in the grand scheme of things, so I decided to skip it. Section 6 is going to kind of seem weird to you guys, okay? Ultimately, though, the thing I need you to keep in mind is this. What we've done to this point in this chapter is we've focused on the first and second derivative test to find, like from a graphing perspective, maximums, minimums, and points of inflections. So even though this is going to kind of seem like we're veering off in a completely different direction, it's all related to the idea that eventually, and what we're going to look at early next week, is we're going to compile all of these calculus-based tools that we're developing right now, and we're going to compile them into the ability to graph very interesting looking functions, okay? So what we're going to talk about today, or what section 6 is all focused on, is vertical and horizontal asymptotes, okay? So no lie, the first several questions on your assignment today are going to be just pictures of graphs that go like this. They're going to have a graph. It's going to have maybe a curve like this, and then another curve like that. And all it's going to ask you to do, I think they're even highlighted, to be honest with you guys. They're going to ask you to identify any vertical and horizontal asymptotes. So you can see in this graph, I didn't draw it particularly well, but let's just ignore the bottom part of this. If you look at this graph right here, it appears to be approaching both a vertical and horizontal asymptote. So literally all you do is you write the equations of those asymptotes. If this right here, if this is at 2 on the y-axis, that is the line y equals 2. So that's your horizontal asymptote. Y equals 2 is your horizontal asymptote. If this is negative 1 on my x-axis, this is the vertical line, x equals negative 1. So your first, like I said, your first several questions today are just going to be pictures of graphs, and all you have to do is identify vertical asymptotes and horizontal asymptotes as just x or y equations, okay? Then we're going to get into the more function-based approach, okay? And again, this kind of seems weird because we're going all the way back to the very beginning, the original building blocks of differentiation that we got into, which was limits, okay? There's a bunch of different limit questions on today's assignment. There's ones like this, okay, where the limit does not exist, because if you look here, like we all remember how to do limits, you direct substitute. If you want to find the limit as x approaches 2 for a function, you plug 2 into the function and you see what you get. But obviously here, 2 is the one value that makes the function not exist, because 2 minus 2 would be 0. There's a handful of these, and I'm honestly, I'm not even sure exactly how these fit in. I guess they could potentially give us a one-sided asymptote. But anyways, this says not to plug in 2, but plug in numbers to the right of 2. So all you do with this is you plug in a hopefully infinitely close number, and then you do your direct substitution and evaluate it. So you don't want to plug in a number far to the right of 2, which would include 3. You want to plug in something really, really close, like 2.1 is just to the right of 2. If you plug in 2.1 here and then you do direct substitution, 2.1 minus 2 is 0.1 raised to the third power. 0.1 raised to the third power is 0.001, so this becomes 3 divided by 0.001. 3 divided by 0.001 is 3,000. So what do we think that tells us? When you do direct substitution there and you plug in a number pretty close to 2, 0.1, you get a really big number. What this tells us is that the value of this limit is actually infinity. Okay, you're going to get some infinite limits today, and that's okay. Technically, what you can say is what we're really getting at here is when you don't get an actual limit, when you say that if I plug in, or as I get infinitely closer to x, I'm getting infinitely closer to infinity. What that's really getting at is the limit itself doesn't really exist. We're not actually approaching a number, and I'm going to explain more about that in a little bit here. Okay? But at any rate, sometimes we're going to get infinite limits. Now, this one right here, the second one, is going to look pretty weird to you. It's the limit as x approaches infinity. So we're pretty familiar with this. We know that you just plug in infinity and you kind of evaluate it. But what's going to happen here is if you plug in infinity to both of these polynomials, you're just going to get infinity over infinity, because infinity cubed is still infinity, because you can't get any bigger than infinity. There's a trick. Okay, there is a trick for evaluating infinite limits of polynomials. Okay, and I think you'll remember it. We first see this in advanced math. Okay, we do it in advanced math, a pre-calculus unit, without actually like pointing out that it's a pre-calculus unit. But the trick for doing this is you take your fraction, anything in your fraction, and you put every individual term over the largest degree of x in the entire fraction. So if you look here, the largest x that we have is an x cubed. What we do is we take this whole fraction, and you see if you guys remember this, we put every single term over x cubed. So we put 2x cubed over x cubed, and then plus 5 over x cubed. Then we do the same thing to the bottom, 3x, whoops, I shouldn't have drawn that so big. Let me scratch that out. 3x squared over x cubed plus 1 over x cubed. And then what we do, once we put everything over x cubed, is we start canceling things off in the individual fractions. Like up here, we have an x cubed on top and an x cubed on bottom. They cancel each other off. On the bottom, we have 3x squared over x cubed. So the x squared cancels off 2 of the x's, but we still have an x on the bottom. Okay? If I clean this fraction up now, this, what was 2x cubed over x cubed is now just 2. Everything else canceled out. This thing has stayed 5 over x cubed. On the bottom, I have 3 over x plus 1 over x cubed. What we do then, I know that kind of seems weird, and maybe hopefully it comes back to us, but what we do then is we do our direct substitution. Now we plug in infinity, and because of the fact that now we have all these little individual fractions, a lot of our fractions are going to disappear, because when you plug in infinity like this is 5 over infinity. What is 5 over infinity equivalent to? It's equivalent to 0. It's a fraction where the top is 5 and the bottom is infinitely large. So if you have a fraction where it's a really small numerator over a gigantic denominator, it's basically equivalent to 0. So here's what our fraction becomes. 2 plus 0 over, if you look at the bottom, 3 over infinity is equivalent to 0, and so is 1 over infinity cubed. So basically, and that's kind of the whole point for that trick of putting everything over the largest degree, we don't actually change anything's value, because all we're doing is the same thing to every part of the fraction. But then by doing that, when we plug in infinity, we get a bunch of fractions that go to 0. So if you look at this, it's 2 over 0, and 2 over 0 is obviously a domain error. What that tells us is that this limit does not exist. You're going to get some limits today that are going to give you domain restrictions or domain errors on your calculator, because they give you a 0 in the denominator of a fraction and they don't exist. Now, would that have been obvious to us back up here at the beginning when we thought it was infinity over infinity? No, we would not have assumed that it was a limit that does not exist, but it will happen. Okay, how does this have anything to do with graphing and with first derivative and second derivative tests? Okay, so first derivative test and second derivative test find us points. Points of inflection, points that are maximums, and points that are minimums. If you think about this, what this is, when we find the limit of a function as x goes to infinity, here's what we're doing. We're saying as x goes to infinity, am I approaching a specific number? Like that. As my graph goes to the right, forever towards infinity, am I approaching a specific y value? So when we're finding the limit as x approaches infinity, what we're actually finding are our horizontal asymptotes. Okay, that's the application here. This is the method for actually finding a horizontal asymptote. So, as kind of our last example here, I have a function. in that function, we could do the first derivative and we could do the second derivative to find the maximums, minimums, and points of inflection, right? What we also need the ability to be able to do is find any horizontal asymptotes. The way that we find horizontal asymptotes is we apply what we just did in this one. We take the function, but we find, is it approaching any specific number as we go forever to the right? Meaning, as we go forever to the right, is there a horizontal asymptote? So, what we do here is we take the function and we find its limit as x approaches infinity for that whole function. 2 minus 2x squared plus 4 over 3x squared minus 5. How do we find this infinite limit? We do the same thing we did up over here. Anything that is a fraction, and that's key to this one, anything that's a fraction or in a fraction, we put it over the largest degree of x. So, the 2 is not part of the fraction. We can only put everything over the largest degree if it's in a fraction, because then we're doing the same thing to the bottom that we do to the top, so we're not actually changing its value. If you put 2 over x squared here, you're taking something that was a whole number, not part of a fraction, and you're changing it. We're not changing anything. We're just changing the way it looks. We're not changing its value. So 2 stays as 2. Everything else that's in the fraction goes over x squared. So 2x squared over x squared plus 4 over x squared. Sorry, that's a little sloppy. On the bottom of the fraction, we do the same thing. 3x squared over x squared minus 5 over x squared. I can write kind of big because this is going to be my last example. So here's what we get. 2 minus. Clean this stuff up. On top, those x squareds cancel. We're left with 2 plus 4 over x squared on top. And on the bottom, these x squareds cancel perfectly, leaving me with a 3 minus 5 over x squared. And once we do that cleanup step, now we plug in infinity. When you plug in infinity, anything that's a fraction that has x on the bottom is now going to be a fraction that has infinity on the bottom, which basically means it goes to 0. This becomes 2 plus 0 over 3 minus 0, which is 2 minus, again, 2 plus 0 is 2 on top, 3 minus 0 is 3 on the bottom. So it's 2 minus 2/3, which is 1 1/3. That's the limit of the function as x goes to infinity. That means that's the function's y value as x goes to infinity. So that's what we're approaching. This is our horizontal asymptote. So there's problems today where you have to find the horizontal asymptote of the function. The way that you do that is you find its limit as x goes to infinity. Okay, I know it's kind of a weird process. Like I said, it's something that we actually introduced in advanced math, this idea of finding horizontal asymptotes this way. But yeah, it's all tied loosely together, well actually tied tightly together in the fact that eventually we're going to be graphing these functions in a very long method, okay, of doing this stuff, but also doing first and second derivative tests to find our critical points, okay? So take some time, look over the assignment. I'm giving you the odds. This time the back of the book should actually be more beneficial than it usually is. So just make sure that you're getting your answers to mesh with the back of the book answers. And shoot me your questions. If I get time this afternoon, I might try and respond to your questions. Otherwise, you can expect a clarification video Monday morning. Okay, guys, have a great day and a great weekend. Stay safe. We'll talk to you guys later.